Go to the next slide. There we go. Thank you. I'm so very honored to introduce this team, and if I may even brag a little bit about what they've done. So NCATS, obviously this terrible pandemic, N3C was put together in April of last year. And NCATS gave a remit to the N3C team that this needed to be up and running in 6 months because the COVID crisis was now, and that not only that they need to get a national repository up to investigate COVID, but that, by the way, the CTSA is made up of many diverse groups, and you can't just use one common data model. You have to be able to harmonize PCORI, ACT, OMOP, and Trinetics. And so I don't think that was really unfair to ask. I think anybody could have done that in a miracle, but in fact, this team somehow pulled this off. Not only did they pull this off, but they continue to really amaze me. The thing I want to also focus on is the harmonization, which is really not generally thought of as particularly sexy, though I think it's very interesting, is actually the foundational piece of observational data. And without good harmonization, both semantic and syntactically, there really is nothing and no way to move forward. So what these folks have done really is truly miraculous. And one thing I'm really excited to also talk about or have Melissa show, and I believe it's her second or third slide towards the end of the presentation, is not only can you harmonize the data and make it interoperable, but you can take it to the next level, which is, and Melissa's going to show you how you can use the harmonized data to actually connect a phenotype to the omics data. So it's really, to us, or to NCATS, it's really a dream come true to be able to use science to define long COVID instead of us just using expert opinions, and use machine learning to delineate different groups, and then connect it to HPO, human phenotype ontology, to be able to see how we can look for the etiology. So with that, I just want to introduce everybody, and really the A team. We are so lucky to have these folks helping us. Chris Shute from Johns Hopkins obviously has been working in data sciences for many years, hard to even express all the things that Chris is expert on, from FHIR to WHO to ICD-9 to terminology services. Kristen Kostya has been unbelievably helpful. OMOP, just an expert, and just been so wonderful in helping us with all the communities. Devera Gabriel, longtime terminologist, expert, not only preclinical, postclinical, but has just been working with the community and helping them understand how do you get through 4 billion rows of data that are now part of N3C. Richard Moffat, informatics, Stony Brook University, his team.
Look what I got.
Who's on the cohort paper, has been instrumental in
A very expensive, fast iPhone charger.
And Emily Path, UNC. I can't say enough about Emily Path. Not only she started our phenotype team and has continued to help that evolve, but helping, right now we have 86 institutions bringing in data to the N3C. I think we have 46 that have cleaned up and are actually visible. Emily has been instrumental, along with Kristen, about helping these folks bring that data in. And finally, Ben Amore from the Palantir team has just, showed us all the importance of visualization and combining ETL with analytics. So I just can't thank everybody enough, and the job you all have done is just wonderful. So with that, I think I'm going to hand it over to Chris and let you all start.
Thank you very much. And of course, there's Melissa too. I would ask, if you want questions, please put them in the chat, and we'll address them dynamically. And of course, leave time at the end. I want to make the point that we can have data, and we can have it basically in two ways. We can have a hobbyist view of it, if you will, where people rummage around in the data and try to find what they want and use it as available. But being available is not necessarily making it useful. Useful data, particularly in science at scale, really requires that it be classified, structured, organized, so that others can use it. And I would emphasize that it's not sufficient that it be classified, in any arbitrary way. It has to be consistently classified so that other people can understand what it means and how it's used. Next slide. We are all familiar with FAIR and the title of this slide, findable, accessible, interoperable, reusable. But what does it really mean to be interoperable? And I submit that the simple answer to that question is that it's harmonized. If the data is not harmonized, it is not interoperable. As Ken said, there are really two kinds: syntactic, or the structure of the data, analogous to using good grammar in a data science kind of context, and semantic, which of course is about meaning, words, terms, concepts, and that the words have to be understandable. If neither of those pertain, the data is not that useful. Both are necessary. Next slide. Forgive the metaphors here. I'm on a Lego theme, as you can see. If we pick a model, and in this context, it's a rocket ship model. If we pick the Saturn V as the standard, and then if we take the Mercury Redstone, the Mercury Atlas, and the Titan Gemini, and we map them to the modern instantiation of a rocket model, we use good grammar to make sure that the parts that fit, and we use understandable words. You can see on the bottom, the historical astronaut capsule maps to the modern command module, circa 1969, in a way that I think can be generalizable and illustrate the concept of harmonization as models and as concepts. Next slide. We're going to anchor our talk today about what we actually did in N3C, metaphors aside. We're going to talk about our origin source, the transformations, and then emphasizing that there were many manual components that had to be done as pre-work, that we built heavily on previous work done by others. And then we turned that manual work into an industrial scale production operation. With that, I'm going to introduce Emily Pfaff from North Carolina. Emily.
Thanks, Chris. So the first step in the N3C pipeline is to obtain data from sites. And when we began N3C, we knew that the key to getting as many sites as possible to participate was to accept EHR data in as many common data models as we could, without forcing sites to undertake difficult transformations on their end. We wanted to make the transformation piece our problem, the N3C problem, to keep things as lightweight as possible for participating sites. Next slide. So with this philosophy in mind, we opted to support the 4 common data models that you see here on this slide. There's Odyssey OMOP, PCORNet, I2B2 ACT, and TriNetX. And accepting data in FHIR format is on our roadmap, just as an aside. At this time, very few organizations are ready to submit data in FHIR format, but we all know that that will change in the future, and we do plan to be ready for that when it comes. But anyhow, for the present, because we accept data in models that sites are already using and maintaining for other purposes other than N3C, sites have very little extra work to do to send their data to N3C. The idea was to make it as convenient as possible. Next slide. So the N3C phenotype team has written a set of cohort identification and data extraction scripts that sites can run locally. And on the right here, you can see all of the model and database variations that we currently support. It's quite a few. And all sites need to do is choose the right script for their environment and run the script. We have even built routines to automatically format, zip up, and securely send the data to N3C if sites choose to use that function. Now, for sites that have questions or need extra help, we offer office hours, which have proven to be quite popular. We purposely keep the meetings informal, kind of lighthearted, to engender a community feeling among our sites. And frankly, they often talk to each other more than they talk to us. So it's been a really great experience. For sites that need more help than that, we offer a white glove service where we'll meet one-on-one with those sites and help them with troubleshooting live. So far, we haven't run into any insurmountable problems, and many of our sites would tell you that their participation in N3C has actually improved the quality of their local data. Next slide. Still, harmonization among 4 different data models is not straightforward. If it was, I know that we would have done this work many years ago. And each of these models that you see here was built for its own purpose. And as such, each model prioritizes different things. I think this example of how each model handles death data is pretty instructive. So you can see that Odyssey and PCORNet both support pretty rich death data, including death cause and whether patients were discharged as deceased. But PCORNet allows you to note that a patient is deceased without providing a specific date, whereas OMOP requires the date. Trinetics and ACT require the date, but they don't add that additional richness to the data by allowing you to add a death cause or a discharge disposition. So when we harmonize all these models to OMOP, I like to say that the data is harmonized, but it's not homogeneous. We can fit all of these into the OMOP convention, but once it's in there, you can still pick out what data came from which model based on what is systematically missing. And it's important that we don't sweep these differences under the rug or pretend they're not there. Instead, we harmonize what we can and provide detailed training and documentation for handling the rest of the differences for users of the data. So now I will hand it off to Devira Gabriel. Oh, sorry, Kristen Kraska.
Okay, I am really excited for Devira to present too. But before we get there, you might be asking, why land in OMOP? And it's a really, really good question. There are lots of amazing common data models out there, and it's really a question about use cases and in a lot of cases, thinking about the future. And I want to highlight something that's somewhat unique to the OMOP common data model. This red box on the orange section is our standardized vocabulary. And you can think of this like a lingua franca, where you can speak in your mother tongue and we take from your source systems into a standard ontology. It evolves as our clinical understanding evolves. There are releases from the OMOP vocabulary team. And this is really an interesting thing that allows OMOP to be very semantically expressive. Next slide. And of course, OMOP evolves as we evolve. We started very humbly looking at comparative effectiveness, trying to find the best method. Boy, were we naive. Suddenly, we realized data standardization was important, and we've begun to evolve to that person-centric model we are today. And I believe that as we continue to have consortia like the one we are in today, you will see all sorts of new types of data come in, such as waveform or molecular sequences, maybe those pesky flow sheets that are quite difficult to standardize. And while I can't confirm or deny that Perseverance is transmitting data back to OMOP, I do think there will be a time when we will continue to evolve to meet other data feeds. And with that, next slide, I'll hand over to Devira, who really has a wonderful story to tell us. Devira?
Thanks. Good afternoon. I am Devira Gabriel. I'm also a research terminologist with Johns Hopkins University and a member of the N3C Data Ingestion and Harmonization Workstream. I'm going to share with you some of the details about this key component of the N3C architecture, the data ingestion and harmonization pipeline. The pipeline is a complex series of software procedures that transform site data payloads to support uniform access and utilization of the extremely rich data set for analytics. The goal of the harmonization effort is consistent preparation of the data, where each step checks for and ensures the data quality, producing a uniform data set that's easy to use. After the data partner sites run the phenotype, extract, and exporter scripts, the extracted data payloads uploaded to a secure site in the cloud are picked up by the N3C ingest server for processing. Next, there's a data synchronization and parsing step that validates whether the data is formatted properly and checks the contents of the payload against its package description or the data manifest. A native CDM check validates the payload is conformant to its source common data model, which prepares and ensures it can be mapped consistently and as expected to the OMOP common data model. Transformations baked into the data harmonization pipeline were carefully curated late last spring in an extensive manual effort representing more than 1,000 person hours over an 11-week period. We brought together a team of data standards and common data model experts who painstakingly reviewed baseline maps provided by Samvit Solutions. In a series of live group sessions, we reviewed each of the 4 source common data models in turn, resulting in customized map sets for each. That ensures consistent implementation of the transformation semantics to OMOP. The pipeline leverages these maps and a dynamic set of vocabulary and code mapping to translate all terms. This is where semantic translation occurs in two parts. First, there are crosswalks that address the static common data model value sets for lists such as gender or encounter types. This is followed by a dynamically generated OMOP mapping table for data encoded in large controlled vocabularies such as ICD-10, LOINC, or CPT-4. The result of this work, the crosswalk tables and mapping code developed for the N3C data pipeline, in total over 2 million possible maps, is maintained and published on a publicly available GitHub repository. Next, the N3C global identifiers are generated. This ensures that as the sites repeat the extraction and submission cycles, and site data payloads replace previous submissions, the data set and the enclave combine records accurately and aggregate longitudinal records for individual patients. There's one last data quality check before being released for use by researchers. Data payloads contributed on an ongoing basis and refreshed in the enclave through the pipeline are reviewed by a team of subject matter experts using robust data characterization and quality visualizations before the payloads are merged into a versioned N3C set. Where I've provided a few details about the N3C data ingestion and harmonization pipeline itself, its most important component is the truly diverse, multidisciplinary team behind its conception and build. We represent industry, academic, research, government, and data standards organizations. We are physicians, nurses, researchers, data scientists, system and infrastructure specialists, and project managers. It's the sum of our collective skills that made it possible to produce this novel and groundbreaking bit of technology. So next up, I'd like to introduce Dr. Ben Amor from Palantir.
Thank you, Devera. So this pipeline that Devera has very clearly outlined needs to actually be deployed and run for each of the 50 or more sites that have currently contributed data. And to do this both quickly and robustly requires some pretty complex technical infrastructure that I'm going to talk about. So we go to the next slide. There were sort of a number of key technical requirements for the setup of these transformation pipelines. The first is that we had complete transparency into the lineage or provenance of each step of the transformation pipelines, and we'll see why that's important in a second. The second was that because we knew the pipelines would be continually evolving and being developed, there needed to be robust versioning and change management applied to the pipelines. Third, in order to guarantee the data quality, there needed to be automated data health checks applied throughout the pipelines. And then finally, because we knew the scale of the data was going to be very large, we needed to have a scalable cloud-based compute infrastructure. So next slide, please. So when you have 50 or more sites, each of which having 100 or more transformations applied during this processing, when you identify data quality issues, you need a way to trace back to exactly where those issues were coming from. And so what we're looking at in the figure on the left is a screenshot of the flow of the data from the raw ingests from the sites through each step of the harmonization pipeline. And each of these steps is being automatically tracked. And this view that allows us to sort of track back and work out where exactly a problem has come from is being automatically generated by the pipeline, by the platform. And so this enables the developers to very quickly identify the root cause of data quality issues. And it also enables these pipelines to be refreshed and updated when we get new data very quickly. So when new data arrives from a site, it can be refreshed in less than 20 minutes. Next slide, please. To address the second challenge, each update to the mapping pipelines for each of the CDMs is versioned and uses software engineering best practices. And so this means that using a deployment infrastructure and UI within the platform, updates to each of the pipelines can be very carefully controlled, tested, and rolled out on a site-by-site basis. And all changes to the logic of these pipelines is documented and clearly transparent. Next slide, please. And then finally, we obviously know that there's going to be data quality challenges and issues that's going to be unique on a site-by-site basis. And so when the CDM mapping pipeline is deployed for a new site, it automatically comes with a set of automated health checks. And these run every time the data updates, so that if the new data doesn't meet the expectations that have been encoded in these rules and these checks, then the administrators of these pipelines are immediately alerted about that fact and can take action to address that. And it prevents that data from flowing downwards into the actual research and analysis ready data sets, and ensures that those always have high quality and high integrity of the data. And I'm going to hand over to Dr. Emily Pfaff.
All right, so I am back again, this time to talk about the more manual side of data quality checking, which actually has quite a bit to do with harmonization as well. So data harmonization entails data transformation, just like Ben was talking about. And with each data transformation step, there's a chance for error to occur, possibly all the way back at the first transformation in the feed from the site's EHR, and possibly within our centralized transformations at N3C. So data quality review is a critical part of the N3C pipeline. And as we bring in each new site, that site's data gets a thorough quality review by a team of common data model and EHR subject matter experts. Data quality review is a part of most clinical data research networks, but there is a difference in what's possible from a data quality perspective when your data is federated versus centralized. Most of the common data models that we've been discussing are federated networks where N3C is centralized. And if you're not familiar with the distinction, in a federated network, all sites harmonize their data to the same model. I'll use PCORNet as an example, but keep the data locally. They don't send it anywhere. So when you want to ask a question of the data or perform a data quality analysis, you send a query or a script to the site, have them run it locally, and then you'll get aggregate results back as a response. With a centralized model like N3C, sites are actually sending their raw data to us. And this allows us to delve deeper when we're doing quality analyses and compare sites with each other rather than being limited to individual aggregate results. Next slide. So I think this is best illustrated with an example, and this is actually a real example from N3C using fake data. So let's say that I send a quality checking query to sites in a federated network, asking them how many COVID-related inpatient visits they've had in the last month. Let's assume these 3 sites are about the same size. They all run my query and respond in aggregate. Site 1 has 43 visits, Site 2 has had 27 visits, and Site 3 has had, wow, 806 visits. Clearly, we have some kind of issue here, likely with how Site 3 defines a visit. And if you try to combine Site 3's data with the other 2, you're going to have a lot of problems during analysis because you're not going to be comparing apples to apples. Now, with centralized data, because we have the raw data available to us, we can dig into this problem a little deeper. We can compare all the sites with each other, as you can see in this table here, and get to the bottom of what's going on. So sites 1 and 2 look fine with inpatient visits with distinct admission and discharge dates. And then when we look at Site 3, we can actually see what's happening. They have a bunch of duplication with multiple visits starting on the same day for the same patient, which doesn't seem quite right. Next slide. So let's walk through how N3C would deal with this finding. And again, this is exactly how we did deal with it because it's a real thing that happened. So first we would discover the issue at one of our thrice weekly data quality meetings. And after looking over a table that would look very much like the one on the right, we would discuss whether we think this is a local issue that the site might need to fix, or whether it's an issue with our harmonization pipeline that we need to fix. In this case, we think it's on the site side because the site appears to be the only one with this pattern. Because we have a close relationship with our sites, I or another phenotype team member will just email the site's tech team, mention the issue, and get their take on it. And when I did this in real life, what the site told me is that that's how their EHR's billing module defines inpatient visits, and they can't change it on their end. That was certainly understandable, but it means that it's on N3C to fix it centrally. Next slide. So if we need to fix it on our end, then the goal is to make Site 3's data look more like the other sites. So it's another layer of harmonization on top of the vocabulary and variable harmonizations that we talked about earlier. Now, I'm really oversimplifying this, but generally we handle this by writing an algorithm that checks for more than one inpatient visit for the same patient on the same day. And where that pattern occurs, the algorithm merges those visits into a single macro visit. Next slide. So once we run that algorithm, we get the behavior that you see here on the slide, where those duplicated visits are merged into one visit spanning the whole time frame. Now the data looks much more like sites 1 and 2, and importantly, all 3 sites can be analyzed in tandem. Now, in this case, the site didn't have to lift a finger other than giving us the explanation for what we were seeing. So the takeaway here is that this incredible ability to do centralized assessment of data quality not only makes things easier for sites, but allows users of N3C to take full advantage of the huge sample size in the enclave. We can analyze not just within sites, but across them. The other important takeaway is something that Ben also mentioned, is that we work very hard to ensure that all our transformations are very well documented, logged, and completely reversible if needed. Next slide. I will close by giving you a few more examples of the kinds of checks that we run, because it certainly goes far beyond inpatient visits. What you're seeing here in the screenshot is a subset of all the different variations on COVID test results that we get from our sites. The counts in each cell allow us to see how many test rows are coming in with each of those result types. We use visualizations like these to check plausibility of sites data when it comes in, making sure, for example, that a site's proportion of positive and negative COVID tests pass muster. We also look at things like average number of rows of data per patient, how well a site conforms to their model standards, their demographic distributions, and oddities like visits that have an end date before the start date. And with that, I will turn it over to Dr. Richard Moffett.
Thanks, Emily. So I'm going to talk about a little bit of unit harmonization, which happens even after the processes that Emily described. So even after this harmonization, we have to harmonize units because data will come to us from sites in different units. Considering body weight here, it could be straightforward to use known conversions to turn all this data into kilograms, for example, using the formula that we all learned in high school and middle school. But since all these units are in OMOP, this becomes really easy to do and really easy to automate. However, some units are missing and or nonsensical. So in this case, we have 2 options. The first one is to contact the site and work with the site, like Emily just talked about, to try and correct the problem upstream. But we've also created a unit inference engine to infer units based on their distributions. So the result of this inference and this part of the pipeline is a concordance of data, regardless of the site, which you can see on the bottom, or regardless of the unit, which you can see in the violin plots to the right. Now you might notice some differences in the violin plots on the right, which highlights a challenge in this process, which is namely that humans measured in grams do not generally look like the same type of humans that are measured in kilograms. So there are some differences we have to account for. As a big picture summary of this whole process, I'm showing you data from the 30 most commonly used labs and vitals. You can see in blue the vast amount of data that's been rescued by the N3C unit inference engine. In dark green is the data that's converted with the easy conversion, so like pounds to kilos. And the light green is data coming to us in the right format in the first place. The blacked out marks data that the algorithm believes the reported unit to be incorrect. So for example, we saw data that came back to us, it was clearly labeled in pounds, but it was obviously kilogram data by the distribution. And so we've saved ourselves some headaches downstream, which would have been really difficult to catch in a federated system. So finally, I'm going to hand it over to Melissa Handel.
Thanks very much, Richard. So I'm going to talk a little bit about some of the harmonization work that we've been doing with the released data set so that we can do different kinds of analytics within the enclave. Next slide. Next slide, there we go. So this work is really focused on analyzing data within the enclave to, really start to think about what are the long-term effects of having a COVID diagnosis. And so what we did in order to start to look at that was really comb through the literature. And in this case, we have 40 publications that were curated and all of their reported phenotypic features for long COVID captured. And then we grouped them into those colored groups there with 7 colored groups. And you can see a blow up of what the sort of heterogeneity of all the terms that people are using in the research literature to describe the phenotypic characterization of long COVID patients. we took these terms and mapped them all to the human phenotype ontology, which is a semantic ontology developed by the Monarch Initiative, and which is led by Dr. Peter Robinson. And in this case, those terms, once they're mapped to human phenotype ontology terms, which are shown there in the colorful grid on the right, you can see terms such as fatigue and chest pain and chills, things that we've all heard about in the news, but now they're semantically encoded using the HPO. And when we take those terms, the column over there on the right for the researcher, we actually curated all those literature terms to the human phenotype ontology and looked at the frequency of distribution in each of those papers for each population of patients that was evaluated. We also curated alongside the patient research group for long COVID, the results of their survey, which is shown on the left, their phenotypic features and the frequency of those features in those patients. And so this is a really interesting way of comparing the semantic, using similar semantics, the results that we're seeing from patient-reported outcomes and from researcher-reported characterizations within the literature. And because the HPO has been translated into layperson-ese, if you will, the terminologies can actually, the HPO terminology can actually be used by both communities. But what's very interesting here is the extreme difference in reporting that we see in the research characterization versus the patient reported characterization. And so after that harmonization is done, we were able to really make that comparison. But we don't stop there. Go to the next slide. So we took the enclave data, and this was led by Emily and Richard. So thank you very much. And they took the patients that we had at least 1 year of clinical history for, that had a diagnosis that had been at least 90 days. And we looked for patients that had differences in their characterization before and after the diagnosis and in that post 90-day period. And the way in which we looked at those patients is we actually, and this was led by Tiffany Callahan, who's a graduate student at University of Colorado, a set of mappings between the OMOP codes and the human phenotype ontology. So we took those same set of over 160 HPO phenotype terms that were curated from the patients and the literature that I showed you on the prior slide, and created code sets from those terms, essentially handles for sets of things that are represented in the OMOP standard. So for example, pain is an HPO term, 0012351, has a series of OMOP codes, like a dozen or up to 25 different OMOP codes that might be related to pain as kind of a sort of handle for all of those codes together. And with those, we curated 160 different code sets that were related to those phenotypic features that are described by researchers and patients in the literature and in the survey. And then running an algorithm to look to see what kinds of co-occurrence in the phenotypic features do we see in those patients, in this case, over those 297,000 patients that could potentially have long COVID. What kinds of patterns do we see in their phenotypic characteristics? And you can see an example of some early results there on the right, where pain, palpitations, paresthesia are a phenotypic profile. We can then take that profile, and because we've integrated within the enclave a knowledge graph developed by Justin Reese at Lawrence Berkeley National Lab, that knowledge graph has information from the literature about genes, phenotypic features, gene functions, diseases, and drugs. But most importantly, it has the human phenotype ontology in it. And so we can associate those graphs coming from those phenotype profiles from the patients, from those almost 300,000 patients, with the mechanistic biology that's represented in that knowledge graph, perform machine learning over the co-located knowledge graph with the clinical data encoded with both OMOP and HPO, and identify drug candidates that may either exacerbate or aid long COVID patients. We can also build predictive models that help us understand what sorts of characteristics of a COVID patient will lead to the long-term sequelae that we're seeing in COVID patients. And so these are other kinds of harmonization functions that can be layered on top of the OMOP encoded data that's released in the enclave. And we expect to see a lot more of this kind of semantic harmonization with other communities. So for example, specifically social determinants of health, there's a lot of ontologies that can also be related in that knowledge graph in the same sort of way, for example. So with that, I think we're going